Thanks. I'll begin again. I'll begin with a prayer actually today. Heavenly Father, we just pray for the second part of the class that you'd help us to understand and just bless this class. Lord, we pray. Amen. Any questions about all this? I mean, why are we doing this? It goes back to the example I showed you at the end of last class. This is part of the machine of solving differential equations, right? We have to be able to undo the transform in order to get back to the solution that we want. All right, so I'm going to, I mean, you can go on like this. There are many other different things that could happen in partial fractions. But this is a pretty good set of examples so far. Oh, I should have left that. What did I have there? What was that? Never mind. I always have some plan about saving it for later for some other example, but we'll just make up another one. So I need to take a little break here from Laplace transforms and inverse transform and go back to a simpler time. So how many of you ever had actually a course in trigonometry? Show of hands. One? Sort of like it was, or was it more like it's just part of the pre-calculus course? Maybe we spent like 4 weeks on it, something like that. I actually had I forget if it was a semester or a quarter course at the community college. I had a course in trigonometry. The book, just a book on trigonometry, right? But even in that course, I didn't really learn what I'm showing you now. And that's unfortunate, but it goes back to this reluctance we have as educators in, at least in the US, of using imaginary numbers to their full extent. Which is, I don't know, I think it's a shame. But so what I want to show you is how to do trigonometry with imaginary numbers. A little bit anyway, just a slice of it. So the fundamental thing is this. E to the I theta is cosine theta plus I sine theta. And so you can look at this, and if you look at e to the minus I theta, what do you get? Cosine theta minus I sine theta, because if we put in minus theta into cosine, it just gives us back cosine again. If I put minus theta into sine, I can pull the minus out because sine is odd, right? So you take these equations and you add or subtract them, right? If I add them and divide by 2, I get that cosine theta is 1/2 e to the I theta plus e to the minus I theta, right? Do you see that? If I add these two equations, the sine terms cancel. I get twice cosine theta is e to the I theta plus e to the minus I theta, right? On the other hand, if I use subtraction, I can get sine theta is equal to e to the I theta minus e to the minus I theta. Now, I mean, if you subtract the equations over here, right? What do you actually get? You actually get 2i sine theta is that, right? So I really have to have 1 over 2i. But there you go. These formulas right here allow us to trade problems in trigonometry for corresponding problems in the algebra of imaginary exponentials. Algebra of exponentials is something you can do. There shouldn't really be any intellectual burden to memorize and to remember these things because they're the usual laws of algebra. For example, what example I'm on? 7? Yeah. For today, example 7. If I do, check this out. So if I multiply sine theta times cosine theta, if I do that in terms of imaginary exponentials, what do I get? I got 1 over 2i e to the I theta minus e to the minus I theta 1/2 e to the I theta minus, or rather plus e to the minus I theta. So I've got a 1 over 4i, right? And what happens when I multiply these? What do I get? I get what's e to the I theta times e to the I theta? Guess what? It's e to the 2I theta, right? The other cross term, this times that, not cross term, the other term with minus theta and the minus I theta, that gives me minus e to the minus 2I theta, right? Then, what do I get from multiplying the other term there? What happens when you multiply, for example, this times that? Plus, what's e to the I theta times e to the minus I theta? It's 1, right? That gives me 1. And if we look at this plus this times that, I get minus 1, right? So what is that? Well, that's 1/2, 1 over 2i, e to the 2i theta minus e to the minus 2i theta. Right? But what is that? Been watching a lot of Naruto lately, so the idea of substitution is heavy. It's heavy on my mind. I'm sorry, all these Naruto-based comments. How many of you guys actually watched Naruto? Nobody? I was talking to myself. Man. You know, you guys, I used to have cultured students, but sorry. But yeah, it's sin. Yeah. Sine. This is liberty. Come on. 1/2 sine of 2 theta. Of course, maybe you already know this, right? The sine of 2 theta is, what is it? It is 2 sine theta cosine theta, right? That's a pretty famous trig identity, you know? Definitely should remember using that in physics 1, right? My larger point to you, though, is I just derived it using algebra, right? Show you another example of this flavor. What if you want to simplify something like the sine of 3 theta times the cosine of 4 theta? Can you simplify this? Right? In fact, you can. Here's how. This is 1 over 2i, e to the 3i theta plus e to the minus 3i theta, 1/2 e to the 4i theta plus, ooh, I made a mistake. Can you guys tell me what it is? Yeah, the sign has a minus. Thank you. That was it. And then multiply. Multiply. So we have 1/2, 1 over 2i, pull those out front, leave them there. And this is going to be e to the 7i theta minus e to the minus 7i theta. Let's see here. Minus e to the I theta plus e to the minus I theta. Right. Or I could rewrite this 1/2, 1 over 2i, e to the 7i theta minus e to the minus 7i theta minus 1 over 2i, e to the I theta minus e to the minus I theta. It always goes back to the boxed equations I have for sine and cosine. Like, we're always looking for that substitution. The game we play here is convert to imaginary exponential, do algebra, and then try to go back to sine and cosine using the standard reductions. Well, the standard formulas, let's say. So what is that? what's this? What's this? Yeah, sine of 7 theta, and then what, minus 1/2 sine theta. Example 9. What if I wanted to calculate the formula for the cosine of, here, let's be lazier. Let's do cosine of A times the cosine of B, like that. Let's just derive the formula for it. How to reduce a product of cosines. Let's see here. So we really got 1/2 of 1/2 e to the I. We've got A plus B, and then plus e to the minus I times A plus B. Here, let me underline which terms I'm using. That's this times this, and also that times that. Then there's 2 remaining terms, which are based on differences of A and B. So I have plus 1/2 e to the I A minus B plus e to the minus I times A minus B. Anyway, I'm trying to show you guys, this is just about as much trouble to derive the general formula as it is to put 3's and 4's there, right? In fact, it's less writing, isn't it? Because instead of having 3 theta or 4 theta, I've got an A and a B, you know? What is this? This is what? This is 1/2 of what? Now, you may have never actually learned these formulas because you may have discovered on your calculator that you could do the problems that you need to do with these formulas without actually using these formulas. Because calculators these days are too smart sometimes for pre-calculus teachers. I probably would be included if I was teaching the course. I probably wouldn't have noticed. But like all of a sudden it hit. I think it was Professor Young. He's like, "Look what this calculator does." So like the regular calculator they're allowed to use completely shortcuts the formula, like the whole problem. And so it's, I mean, part of the problem, they're trying to give problems which teach students how to understand and unwrap these formulas. But the students aren't forced to use the formulas because the calculator just does it for them. So they never really learn the formulas, unfortunately. Anyway, so there it is. The product of cosines is actually the sum of 1/2 of the cosine of the sum and difference of the arguments. Example 10, and then I'll stop this trigonometry refresher. But example 10, what if we had the sine of A times the cosine of B? What would the formula be in that case? I'll give you guys a minute. See if you can work it out. Let me do it in my head. 1/2, well, oh yeah, 1/2 sine of a plus b plus the sine of a minus b. Can I tell you a secret? I didn't do what you're doing. I did this. See, if you just differentiate this identity with respect to a holding b fixed, you get that one. Right? You wanted me to zig, but I zagged. Sorry about that. Or if you like partial a, I mean, there is more bags. I mean, there's more tricks in the bag than just mechanically using these formulas, but it will also get you there. I mean, you should get to the same thing if you do it right. You notice the difference with sine times cosine in what you guys were doing, I assume, is you had a residual I left over, right? You had like a 1/2I sitting out front. That's going to be needed to convert these back to sines. So when you do these sorts of calculations, if you have a leftover I out front, that means you're going to get sines. If you don't, probably means you're going to get cosines, you know? And then finally, one other formula, just to make sure it's fresh in our minds. This one also can be, here, I'll actually show you. Check this out. So if I have e to the I theta, e to the I theta times e to the I beta, what would that be equal to? Check it out. This is e to the I theta plus beta, right? But you can also see other things here. This is cosine theta plus I sine theta. And that, of course, is cosine beta plus I sine beta. Now, that is going to be, well, multiply that out. What do you get? You get cos theta cos beta minus sine theta sine beta plus I times what? I times sine theta cosine beta plus cosine theta sine beta. Just multiply it out. Collect real and imaginary terms. I squared is minus 1. But this, of course, is also what? That's the cosine of theta plus beta plus I times the sine of theta plus beta. I personally found this very helpful when I was at your stage in my education because all of a sudden I had this tool which I could use to remember the adding angles formulas. If I was ever in doubt about how the adding angles formulas for sine and cosine went, I went back to this. See, because this is the real part, right? And this is the real part, which means that cosine of theta plus beta is cosine theta cosine beta minus sine theta sine beta. That's the adding angles formula for cosine, right? And on the flip side, this imaginary part has to match that imaginary part. So we have sine theta plus beta is sine theta cosine beta cosine theta sine beta. Now, I'm not suggesting that you have to do this every time, but for me, working this out a few times just cemented in my mind the adding angles formulas for sine and cosine, right? So these you should know for sure, right? We need these sometimes. Cosine of theta plus beta, cosine theta sine theta, I'm sorry, cosine theta cosine beta minus sine theta sine beta, and the sine of theta plus beta is sine theta cosine beta plus sine, goodness gracious, sorry, plus cosine theta sine beta. So these, of course, these we need to know, right? I mean, I'm not telling you anything terribly new. Here's a fun thing, maybe you didn't notice before, though, in terms of memorizing and just remembering and being fast on your feet about things. Can you get from here to here in any way? Like, how about this? What if you, I don't know, how about, what happens if you differentiate with respect to theta? See, differentiate with respect to theta gives me minus sine theta plus beta, minus sine theta cosine beta, minus cosine theta sine beta, multiplied by minus 1. There it is. If you know one, you know the other. Like, why didn't anyone tell me this in Calculus 2? That would have made it too easy there. I'm not going to tell them next semester. Are you kidding me? No way. I can't let the grade distribution get too high. They always fuss here, right? They're like, you're great. You have given too many good grades in this course. You need to fix that. Otherwise, we can't have that. I'm just kidding. That would never, ever happen. Sorry. All right, enough trigonometry. Do you guys, I hope you feel empowered, right? Is this a safe space to do trigonometry now? Math march. Oh, I have a math march. I'm sorry, I was reading the good touch, bad touch poster outside the elevator, and it's influenced my... We're having children's camps right now, so there is a, you know, don't be bad to the children poster, because that, of course, will stop those people who are such people. Anyway. Kind of like, well, anyway, shut up. No good can come of these comments. Let's see here. Oh, yes, we don't need some more. So all of this, guys, really just for the sake of the following example and or examples like it. Example 12. How would you calculate the Laplace transform of, I don't know, sine 3t, cosine 4t? I think I only did really easy Laplace transforms with you last time, right? I should pick up the pace here and show you a couple of actual kind of difficult ones. I mean, Laplace transforming never gets that hard, in the same sense that differentiation's never quite that hard. It's pretty much, if you're asked to do the problem, you should be able to do it, but I guess this is a little bit harder. I mean, if I differentiated these, it'd be easy, right? I mean, I just differentiate them, right? But here, the trouble is, we don't know the Laplace transform of sine times cosine, do we? No, we do not. But if we use trigonometry, we can convert this to what? I worked out over here. It's actually 1/2 sine 7t minus 1/2 sine t. And then at that point, we're like, yay. So that's just, what is it? It is 7/2 times s squared plus 49 minus 1/2 times s squared plus 1. Hooray, done. Here, let me make it horrible. You're like, there's no need. Well, I might give you a homework problem like this, so I should at least have the decency to do one. Right? Example 13. What if we're asking you to take the Laplace transform of, like, t times the sine of 3t times the cosine of 4t? Now here I have to use a theorem, right? So this is minus DDS of the Laplace transform of everything except for the t, right? But in example 12, we learned the Laplace transform of sine times cosine of 3t, 4t respective is this. So I'll pull the half out because it's common. And we've got 7 over s squared plus 49. Just when you thought you'd escaped the quotient rule, it's back. Well, I mean, or you could do substitute. I mean, however you want to. You calculate the derivative how you see fit. I'll calculate it how I see fit. And anyway, it's math, so there's an answer. So that's 14s over s squared plus 49 squared. There's a minus that I'm missing. And then plus 2s over s squared plus 1. The minuses and the 2's can cancel. I'm going to simplify just a little bit here. So that's 7s over s squared plus 49 squared minus 1 over s squared plus 1 squared. Hooray! Now think about this for a second. Does it make sense that our answer has a quartic, a fourth order polynomial in s in the denominator? Does that make sense to you? Yeah. Oh yes, thank you. There is an s there. Sneaky s. There, put it back. I mean, what differential equation would take t times the sine of 7t and t times sine t as solutions? What order differential equation would that be? To get t times the sine of 7t and t times the sine of t as solutions, need d squared plus 49 squared and d squared plus 1 squared in the operator factorization if it's a constant coefficient ODE. In other words, this would be attached to like an 8th order problem, because the differential equation, which would pick up t times that sine and t times that sine as solutions, would be, you know, d squared plus 49 squared times d squared plus 1 squared times y equals to 0. That would pick up t times sine of 7t or t as solutions. Now, if you were to make a common denominator here, right? If you were to make a common denominator here, you would have an 8th order thing. You'd have s squared plus 49 squared times s squared plus 1 squared as the denominator, and that would be the characteristic equation which popped out of taking the Laplace transform of that thing. So, yeah. You don't see these too much in applications, is my point. Like, I don't know. If you asked me for what's a you know, physical application of an 8th order, what's an 8th order ODE that appears in a natural physical application, I'd be hard pressed to find one for you. But these things do appear in the math, and anyway, it's not impossible, it's just unlikely. Any questions? So sines times cosines, we need to be able to convert to sums of sines or sums of cosines to do it. And this math is also useful because, you know, another application of the trigonometry would be this, right? Well, it's too late. I have to go on. I was thinking back to where we rewrote c1 cosine plus c2 sine as a times the sine of an argument plus a phase angle. That's also using the adding angles formulas in the place where we used them earlier. Okay, so changing gears here a bit, let's talk about the discontinuous functions. So how do you take the Laplace transform of a discontinuous function is really the question, right? f is discontinuous. Now, discontinuous, typically piecewise defined. All right. So the fundamental piecewise defined function is the unit step function. So here it is, u of t minus, let's say, t naught. What is this? This is 1 if t is greater than t naught, and it's 0 if t is less than t naught. I don't know what it is if t equals t naught. It depends on what book you're looking at. You make it whatever you want. You can make it a half if you like. I mean, whatever. I'm not even going to address it, okay? So I just, whatever it is at t naught, I don't care. Be fine. For the sake of discussion, let's suppose it's 0. I mean, whatever. I'm sure there is a reason to make it a half, probably, but if we were doing more with Fourier and things, but all right, unit step function. What's the graph of this look like? Kind of boring, right? T, u, so it's 0, right? La 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 0. And then you hit t naught, and then it becomes 1. So one of the things you can build from this, example 14. I should probably restart the numbering. Oh well, it's kind of fun to have example 14 though. If I do something like, suppose that T1 is less than T2 for the sake of discussion, right? And what if I think about graphing, so here's my T1, here's my T2. Let's graph u of t minus T1 in green. U of t minus T1 then. Right? Guys with me? What's the graph of u of t minus T2 then? I'll do that in red. U of t minus T2, rather, is in red, right? What if we define g of T1 comma T2 of t as equal to u of t minus T1 minus u of t minus T2? And if I was to graph that, and let's see, some seldom used color. What color would you like? It's like orange or pink? I don't know. Here's my orange. Wouldn't use this orange. Orange marker is probably lonely. I haven't seen anybody in a while. Let's see here. So if I take the difference of the green and the red graphs, what happens? Whoa! Did you do that with your mind? If so, so here it is. It's 0, right? Because 0 minus 0 is equal to 0. Up here, between here and here, 1 minus 0 equals to 1. And then over here, it's 0 again because 1 minus 1 equals to 0. So if you'll free me from this cluttered picture, the graph of this is just, it's 0, and it's 1. And then these vertical lines we draw for artistic purposes, but technically they're not part of the graph because, of course, it wouldn't be a function. It is a function. This is called the gate function. On, let's say, t1 to t2, something like that. So let's say the gate function on an interval should be the function which is 1 on that interval and 0 elsewhere. My point to you in this example is that we can build the gate function from the difference of unit step functions. It's not an especially exciting observation, but it's true, right? You guys with me? You're not against me, are you? Sorry, I may have been watching too many comic book hero-based shows lately. Whoa. That sugar was not mixed in. Yowzers. Whoa. All right, so. Example 15, let's put these gate functions to work. Suppose we have f of t defined piecewise as follows. T for 0 less than t less than pi, and then sine of t for t for pi less than t less than 2 pi, and then e to the t for t greater than 2 pi. It's very simple. You can use gate functions. All right, gate functions give you a formula for this. So I could I just do t times the gate function from 0 to pi of t plus sine of t times the gate function from pi to 2 pi of t plus e to the t times the gate function from 2 pi to infinity. Now, we don't actually have good formulas for the gate function in Laplace transforms. The theorems I'm about to derive for you, it will take all of about 3 minutes to derive the theorem, but I'm doing this first so that we understand what we're doing better. The theorem we're about to discover is all in unit step functions. So we need formulas in terms of unit step functions. So while that is conceptually very, very simple, and why I'm showing it to you, ultimately we need unit step functions for calculation. So we have to convert back to the unit step functions. So this is like t times u of t minus pi. How's it go? I've already forgot. Which one do I? Oh, yeah, sorry. So it's u of t minus u of t minus pi. So I turn it on at time 0, I turn it off at time pi. Think of it that way. And then sine of t, you have turned it on at time pi, t minus pi, turn it off at time 2 pi, t minus 2 pi. These are switches, mathematical switches. E to the t, and this one we just kind of leave the light on at time 2 pi. We just don't ever turn it off, t minus 2 pi. That just puts this exponential non-zero out to time infinity. Now, this is also not appealing for the purposes of Laplace transform. What we need to do is one more step, and then we'll come back to this example, although I'll probably regret it. So we should group things together. I've got t times u of t plus parentheses sine of t minus t times u of t minus pi. Let's see here. Plus e to the t minus the sine of t, u of t minus 2 pi. Now, if I wanted to confuse students, I would always make a habit of going straight from the piecewise defined function to what I just wrote and never explain it. And I would tell them something like, it's not that hard, figure it out. So I assure you, there are professors like that out there. But I think it's nice to have some discussion of how we get to that formula. Yeah. At the same time, I do allow you to go straight to this in your own work, if you understand it. Right? I mean, once you really, really understand the method, you can write down what I underlined in blue without the other stuff, if you understand. All right, so what's that theorem that we need to work out? The theorem concerns what is the Laplace transform. You see what we need then? Basically, what this shows you is that to understand the Laplace transform of a discontinuous function, it really suffices to understand what's the Laplace transform of like a function times a unit step function, right? If I can understand what's the Laplace transform of a function times a unit step function generically, then I can use linearity to take the transform of this. So a good example of where abstraction pays off big time. It's much easier to derive the theorem for an arbitrary function and an arbitrary unit step function than it would be to derive it for any of these specific ones. That's abstraction. So theorem, and we'll discover the theorem as we calculate it here. What happens if we take the Laplace transform of f of t times u of t minus a? All right. By definition, that is the integral from 0 to infinity of, what is it, e to the minus st, f of t, u of t minus a. And of course, we're assuming that f is well behaved. It's got to be exponential order alpha and so forth, yeah? All right. Now this integration is very, very easy all the way up to time a. What's this function all the way up to time a equal to? What's the unit step function before time a? Come on, you guys know. Oh, fine, I'll say it. 0, right? Unit step function 0 before time a. So integrate 0, what do you get? 0. So we can safely, and what is it after time a? It's 1, right? So this is just e to the minus st f of t dt by the definition of the unit step function. Now at this point, what we want to do is make a substitution that changes it back to a Laplace transform. The Laplace transform involves an integral from 0 to infinity, right? So I need to make that a go to 0 somehow. So we should make a substitution. Let's say w. If we put w equal to t plus a, then w of 0 is equal to 0 plus a is equal to a, right? And dw is dt. And what's t equal to? W minus a, right? So there's my integration substitution, a w substitution. I'd usually call it u, but I don't want to make you think about the unit step function. So I'm using a w. And how about infinity? If t is infinity, w is infinity plus a, right? But contrary to school ground taunts, infinity plus a is not more than infinity, right? So it's just infinity again. You guys never had these arguments about like who had the largest number? No? Okay. And some wiseacre would be like, infinity times infinity. Little did you know that you were on your way to calculus in those days. Let's see here. 0 to infinity, and we have e to the t. What was t? Oh, w minus a. Minus s times w minus a. F of w minus a, I suppose. And dt was dw. feel like I did something wrong. Let me think about this for a second. No, it's fine. I just need to stick with the program here. So that is the integral from 0 to infinity of e to the minus sw times e to the as e to the as f of w minus a dw. Of course, we could, I mean, w is a dummy variable of integration, right? So you could just as well write that with t's to make it more familiar, if you like. I mean, this is equal to the integral from 0 to infinity of e to the minus st times e to the oh, I'm an idiot. So this e to the as, right? We can pull it out. E to the as good grief. E to the minus st. I already wrote that. God. E to the minus st f of t minus a dt. There we go. Finally. Now that is exactly e to the as times the Laplace transform of f of t minus a of s. So there you go. It took me a lot of time, but there it is. The Laplace transform of f of t times the unit step function at t minus a of s is equal to e to the as times the Laplace transform of f of t minus a of s. I mean, have anybody had your book on you? There's a sign here that's just, that makes me pause before I drill a wrong formula any further into your brain. Make sure I have not made a sign error here right quick. What section are we in? Oh, 7.6. Yeah, so I have made a sign error. Oh, wait a minute, no. Well, I think I'm supposed to have Theorem 8 is not quite helpful to me. Equation 8 should be what we just derived. Yeah. So if you look at equation 8, you can see I've done something askew. Let's try to find the source of my error. Equation 8, let me tell you what equation 8 in the book says, okay? It says that the Laplace transform of g of t times u of t minus a of s is equal to e to the minus as times the Laplace transform of g of t plus a. So this is equation 8 in section 7.6, which is what I'm trying to derive right now. Using f instead of g, it's not a big deal. Oh, I'm an idiot. Look at this. If t is equal to a, what's w equal to? Well, I put t equal to 0 and I got w equals to a. Well, that's great, but the original integral has t equals to a as its starting point. This is dumb. What I need is that w of a is 0, right? So what should it shouldn't be t plus a, it should be t minus a. If w is t minus a, that means that t is w plus a. Right? And that makes all the difference, because then we get w plus a instead of w minus a where I wrote it in here, which gives me e to the minus as up front and f of t plus a inside. So sorry about that. Really, it's just calculus 2. I just messed it up. Again, equation 8 is correct, right? Now, there's a related theorem here, right? This is what let me erase the offending boxed equation. Let me introduce yet another letter, h. Suppose we had h of t minus a equal to g of t in the theorem I just worked out. What we would have? Laplace transform of h of t minus a, u of t minus a. What would that be equal to? So I'm just saying, apply the theorem using h of t minus a equal to g of t. So I have e to the minus as, right? Times, what is it, the Laplace transform of what is it? F of t plus a, right? I'm sorry. I need to make up my mind. Am I going to use the theorem I just proved, or am I use the boxed equation? I'm going to use the boxed equation, okay? So let me erase the theorem so we're not tempted to look at it. There we go. So we have proved this equation 8 with what I just erased. And if we put h of t minus a equal to g of t, then what is g of t plus a? It's just what? H of t, right? So this is a very useful formula. In fact, it's even more useful if you take the inverse Laplace transform on both sides. What this says is that the inverse Laplace transform of e to the minus as times f, well, let's say times h. Oh, I can't make up my mind. Find h of s. What is it equal to? It's equal to h of t minus a times u of t minus a. So this actually gives me a nice, equation 8 I used to take the Laplace transform, all right? This one I just boxed in, I forget the number of it in the book, but this, I need to give it a name. I don't know, let's call it Hector. There. Hector gives us a way to take the inverse Laplace transform when there are exponentials floating about in the S domain. It's a little bit tricky how it works. Exponentials in the S domain mean discontinuities in the T domain at the corresponding points. All right, well, anyway, we have all the ingredients we need to go back and try to do example 16, right? Example 16 is to take the Laplace transform of example 15's function. So one of the things I should point out before I get too far into this, what happens with a equals to 0, special case? What's the Laplace transform of like g of t times u of t? Kind of silly to even write what I'm writing. I'm just writing it once to get it out of our system. As you can see, nothing happens, right? I mean, so don't sweat taking the Laplace transform of a function times the unit step function at 0. That's essentially built into our formalism already. So the Laplace transform of that is just the Laplace transform of t. What's the Laplace transform of t? That would be the Laplace transform of the direct delta function. Here, 2. Oh, that's t squared. I'm an idiot. 1. 1 factorial, also known as 1. N plus 1, also known as 2. The Laplace transform of t is just 1 over s squared. So that's the first piece. Great. Then I do what? Plus, and then I got to use my equation 8 with a equals to what? The first piece has a equals to what? Pi. See? Pi. A is pi. And I'm supposed to take the Laplace transform of sine of t plus pi minus parentheses t plus pi of s. So I have to take the thing that's multiplying the unit step function and shift it, as equation 8 tells me. Plus e to the minus 2 pi s, Laplace transform of e to the t plus 2 pi, minus the sine of t plus 2 pi. Now this problem is a little bit forgiving because, well, I guess it's not super forgiving. What happens when you add pi to sine? Where does that take you to? Negative sign. Very good. How did you know that?
If it's like sine of pi over 2, and you add pi to that, sine of 3 pi over 2.
Ah. So you just thought about a point. Very good. I mean, the other way you could do it would be the adding angles formula, right? There's to be sine t cosine pi plus sine pi cosine. So like cosine pi is minus 1. So adding angles formula is another way. You can think about shifting the graph left or right. Well, shifting the graph left pi units, it brings you to minus sine. Anyway, one way or the other, you need to know that that's minus sine of t. And then, of course, minus t, minus pi. Nothing more to do there. And then we have plus e to the minus 2 pi s. Let's see here, Laplace transform. And here we got to do some algebra. See, that's e to the 2 pi times e to the t, right? Simple enough. What's the sine of t plus 2 pi?